No.
Oh my word, yes.
Oh, that's quite nice.
Oh, there you go. That suits you. Hello and welcome to Physics Chat. I am Susanna and I'm back with my fantastic co-hosts Sergi and Joe, ready to do some more chatting. Physics Chat is a show where we ask what it's like to be a modern day physicist and hear about the exciting research that is currently being explored. On today's show, we have the absolutely hilarious Arthur Tolley. How are you, Arthur?
I'm good, thank you. Yeah.
Brilliant. Arthur is a second-year PhD student who is currently researching gravitational waves at the University of Portsmouth. I have the huge privilege of sharing the office with Arthur. Well, I think it's a privilege given the fact he's rearranged our office at least 3 times. So Arthur, tell me, who is the funniest person you know and why?
That's a very good question. Recently, I've taken quite a liking to the humour produced by myself. I am one of the funniest people I know. I would dare to say the funniest person I know. It's a tough one because there are quite a few funny people in our office, especially you, Susanna. You're quite funny all the time. So unfortunately, I've got you beaten.
Okay. Arthur, could you explain to the audience how you ended up doing a PhD at the University of Portsmouth?
Yeah, so when I was at school, I really enjoyed physics. It was one of my favorite subjects. For my A-levels, I chose physics, maths, and government and politics, which is another one of my interests. When I was talking to kind of one of these sixth form careers counselors, they gave me the really great piece of advice that physics, you can't get a job with physics. It's not very good. And this was quite detrimental at the time. So I applied for electronic engineering degrees and my results day came around. I got a B in maths, a C in physics and a C in government and politics. So I realized that I didn't actually want to do electronic engineering because that is a really, really boring subject. And instead I wanted to do physics. So I got on the phone on results day and was calling up various universities. The University of Portsmouth was one of them. They accepted me onto the MPhys physics course at the time.
So what does your daily life as a physics PhD student look like?
That's a good question. At the moment, we'll do like an hour by hour schedule. Wake up at like 7 o'clock, you know.
One eternity later.
Sometimes I'll leave at 5, sometimes I'll leave at 8 in the evening, but it's not like I'm overworking myself because I'll just pay myself back those hours during the rest of the week, things like that. It's quite chill.
Brilliant. That sounds really good. So could you just describe what your research is on as well?
I'm part of the LIGO scientific collaboration, which is kind of the conglomeration of all the research scientists that deal with gravitational wave detectors. So these are specifically the 2 gravitational wave detectors in the United States. So there's one in Hanford in Washington State, so in the Northwest, and then there's one in Livingston in Louisiana State, so in the Southeast. And these gravitational wave detectors made history in 2015 for the first detection of gravitational waves. But as with any experiment, the data is not perfect. So we have these things called artifacts or glitches within our data, which are kind of noise within the data, which is caused by things that aren't gravitational waves. Specifically, what my project is looking at is one of these artifacts called scattered light. And what this produces is kind of an arch-like shape within the gravitational wave detector output. If one of these artifacts occurs at the same time as a gravitational wave passes through the detector, what will happen is this artifact will kind of overlap a gravitational wave signal, and you won't be able to confidently say whether it is a gravitational wave signal or not. So if we remove that scattered light artifact, we're able to make that decision more confidently. And it's going really well.
Good. On a previous physics chat, we did chat to Simone about gravitational waves. But for those who maybe aren't up to speed, can you just quickly describe what a gravitational wave is as well?
I can try, sure. So gravitational waves, analogously, people always talk about kind of the ripples on a pond. So you can imagine a pond, the water within a pond is actually our kind of space, the space around us. And what happens is when you throw a stone into a pond, the ripples kind of propagate outwards. Within our analogy, those ripples and the stone are caused by two very massive objects colliding with each other and forming an even bigger object. So yeah, the gravitational waves themselves actually kind of change how our space-time sits in a way. So as the gravitational wave passes through, it will stretch the space-time and then squeeze it, kind of as the wave is going through. So if you look at the ripples on a pond, you can see peaks and troughs. As this passes through, it will squeeze and stretch space-time, only a very, very small amount, nothing to be concerned about. But yeah, it means that we have to have very sensitive machines to detect these gravitational wave signals.
You describe these events, they sound pretty chaotic. Do you have a favorite gravitational wave event at all?
I think there's actually quite a few now, very significant events that have happened for gravitational wave signals. For instance, the very first event that we saw in September 2015 was actually really loud. It was like unbelievably loud, so loud that they thought it was fake because somebody had just gone in and like ejected a fake signal, and they're trying to convince people that it's real so that they're on their toes because they've just started looking for these gravitational waves. There was this unease at the time where it was like, oh, is this a real signal? Is it not? Because again, it was really loud. It looked exactly like you would expect a gravitational wave to look, and it had been seen in both detectors, which is a key kind of aspect of confirming that it's a real detection. It was just before I started my undergraduate degree, so I think we definitely had a discussion about it in one of our physics A-level chats. So it has to be kind of one of everyone's favorite events because it was just so spectacular at the time for how it came about.
Great, fantastic. And as Joe said, this is the second time in physics chat that we talk about gravitational waves. So I have a big question for you. Why should we care about gravitational wave astronomy, and why this new and very recent field is so important?
Yeah, so detecting gravitational waves from one of these events is actually really important when we are trying to understand these objects themselves. So if you look at black holes, so these gravitational wave signals themselves, actually the way that they're produced, they kind of do escape this black hole event horizon so that you can actually make detailed inspections of these properties of the black holes that you see. So we measure things like the mass of the black hole, the spins of the black hole, and then the orientations of the two black holes within the system.
Yeah, it's amazing. I heard someone saying that gravitational waves are like new glasses that astronomers and physicists can use, and with these glasses we can see a lot of new things that we didn't think they were there, and this has been proven by the enormous amount of things that we found since the first detection. So yeah, I think it would be interesting, Arthur, if you could explain how a gravitational detector actually works.
Yeah, so a gravitational wave detector is what we call an interferometer. So we're using the interference between light itself to actually measure changes caused by these gravitational wave signals. So what happens is we have a very powerful laser kind of at the beginning of our interferometer, which fires out a laser beam, and that laser beam will strike a beam splitter. So this beam splitter splits the laser up into two components, one going one way and the other one going the other way. Those two directions are perpendicular to one another. These two beams will travel up the arms, which in LIGO are 4 kilometers long. And at the end of each of these arms is another mirror, which reflects the light back down to the beam splitter. So these two arms are the exact same length. The gravitational wave comes through and it stretches one arm of the detector while squeezing the other arm. And this creates a difference in the lengths of the arms. So when the two beams come back to the beam splitter, they're not actually cancelling out perfectly. You'll see this characteristic pattern to the gravitational wave signal. And then hopefully you'll see it in both detectors at the same time. And you'll be able to say, yep, that's a gravitational wave signal right there.
Yeah, it's really fascinating that how these interferometers work. And it's actually really interesting because we can understand this with physics that we learn in high school, which is constructive and destructive interference of waves. and yet the detail and the precision of these big machines is incredible. So maybe going in that direction, could you tell us how your research is improving these interferometers, these detections?
Yeah, so I think one of the big things that I said before is that you need this kind of coincidence in two detectors at the same time. So to confirm that it's a real signal and not just random noise in the data, you have to see it in the Livingston and the Hanford detectors to say, yep, it's at the same time. Obviously, gravitational waves travel at the speed of light. And so there's a time delay between those two detectors, depending on where the gravitational wave signal is coming from as it travels kind of through the Earth. But if you don't see this coincidence, it's a lot harder to say whether this is a real gravitational wave signal or not. So when you have a signal in one detector, but in the other detector, there's an artifact or a glitch that's covering up the other signal, it ruins your confidence. So when there's scattered light, you can hopefully remove that scattered light and reveal the signal underneath.
We've been talking about LIGO, which is based on the Earth, but could you maybe explain us what is the future of gravitational waves?
Yeah, so gravitational wave detectors, as you said, are currently on the Earth, which means they're affected by things that are on the Earth. So you have seismic motion from the ground moving, you have earthquakes, you have the weather. So some of the detectors are so sensitive that they can actually feel the waves pushing against the land when at the shore. So to counter this, what we have come up with is two different experiments that I'm aware of at the moment. The first one is LISA, so the Laser Interferometer Space Antenna. And the key word there is space. So it's going to be a triangular arrangement of interferometers sent up into space, where it's going to sit some 15 million kilometers away, I think. And this means we'll be able to see things like really high mass black holes. So potentially the supermassive black holes at the center of the galaxy merging with other black holes and objects to produce gravitational wave signals that are really low frequency. The other gravitational wave detector for that is the Einstein telescope. So this is going to be built somewhere in continental Europe, but it's going to be underground. So I think, again, it's going to be a triangular configuration gravitational wave detector, but it's going to be underground, which limits it from some of these seismic effects.
That's amazing. Thank you.
Gravitational wave astronomy is such an exciting field. I didn't realize they had the Einstein telescope and LISA planned in the future. Also, thank you so much for being on the show. I thought it was so inspirational that despite your average grades, with hard work and dedication during your undergraduate degree, you went on to complete a physics PhD. So all the best for you and your PhD. And again, thank you so much for being on Physics Chat and for talking about your interesting research.
Thank you for having me.
We hope you've enjoyed learning about the planned gravitational wave detectors. Let us know in the comments section what your favorite gravitational wave detector is. Sergi and Joe, what are your favorite gravitational wave detectors?
That's an easy one for me, actually. I think the LIGO came a bit too early for me. And also in my field, we're very interested in these low frequency gravitational waves. So yeah, the answer is LISA.
Fine, I'll stick up for LIGO then. I think it's cool. The original ones, the ones that actually did it, got the first detection. So I'll go with them.
Nice. Brilliant. Well, Joe and Sergi will be back for some more physics chat soon. But in the meantime, keep writing. Bye.
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 I am one of the funniest people I know. Which are 4 kilometers.
Yeah, 4 kilometers.
Yeah.
Oh yeah. I don't remember that.
Despite you being stupid as you still managed to get a PhD. You can create a more representative. What's the word? Representative.
Representative.
You were right the first time. You're representative.
Okay. You can wait, what was I saying? So if you remove these scattered light artifacts from the data, you can create a more representative. that was right.
That was right. Yeah.
Bloopers.
I just had to check.
Representative.
Representative. Yeah.